Greetings, my name is Wilson and my matrix number is B112510205 and I am from BELK course. Today I am going to give an introduction about a transfer function, which is h omega describe how a circuit responds to different input frequencies. It is also defined as the ratio of the phasor output y omega to the phasor input x omega. The board plot is a graphical method to visualize the frequencies response. It separates the response into two plots, which is magnitude in dB and also phase in degrees. Both plot against log frequencies.
Hi, my name is Muhammad Nazri bin Zali. Today I want to explain about obtain transfer function to one plot method. To obtain the board plot from a given transfer function, the transfer function is first expressed in its standard board form. The system gain, pole 0, and corresponding corner frequency are then identified. As this parameter define the frequency response of the system. Next, the magnitude and phase equation are derived by substituting S with JW. The magnitude and phase response are then evaluated over the select frequency range. Based on this calculation, the magnitude and phase board plots are constructed using a logarithm frequency scale. Finally, the gain, crossover frequency, phase margin, and gain margin are determined to assess the stability of the system. Overall, this method provides a systematic approach for analyzing the frequency response and stability directly from the transfer function.
From the given question, I am going to explain on how to convert the transfer function into the general state to general standard state to get it ready by a board plot analysis. As we can see here from my calculation steps, we can start with the original equation, which is h omega is equal to 300 j omega over j omega plus with 5 times with j omega plus with 20 square. To get the general state, we must make the constant term inside each bracket equal to 1. Firstly, I took the term which is j omega plus with 5 and factor out a 5, giving us 5 times with 1 plus j omega divided by 5. Next, for the term of j omega plus with 20 square, I have factored out the 20. The entire bracket squared, pulling out the 20 means we have to square it as well, which is 20 square, or we will get the answer 400. This will leave the answer to 400 times with 1 plus j omega over 20 square. Now we have to substitute this back into the denominator and combine our constants. By 5 times with 400, it will give us answer 2000. And finally, we must divide the numerator constant 300 by this 2000, which simplifies beautifully to get exact 0.15. This will give the final answer to h omega equals to 0.15 j omega over 1 plus j omega divided by 5 times with 1 plus j omega over 20 square. From the final form, we can easily read the exact characteristic which need to be drawn for our magnitude plot. Our system gain k is 0.15. The j omega is the numerator, which gives 0 at the origin, which creates an initial upward slope of positive 20 dB decay. In the denominator, we can clearly identify our two corner frequencies: a simple pole at omega equal to 5 radian, which flattens the slope of 0 dB decay, and a second order double plot at omega equals to 20 radians, which introduce a sharp drop of negative 40 dB decay. This completely sets up everything we need to board magnitude. That's all from me. Thank you.
Assalamualaikum, my name is Muhammad Nazmi Nawfal bin Wahab. My number matrix is B1125102842. Today I want to present for assignment advanced electrical circuit. So my part for assignment advanced electrical circuit is magnitude board plot. So before we go to the plot in graph, we should make an equation. Okay, so first 0.15 equals to k. So refer the k. The graph in k is straight line. So for the equation, 20 log 10 times k. So we got the answer is negative 16.48 dB. So for the number 2 is JW over power 1 equals to 1. So for the graph, we refer for number 1 is like this, go straight. So for the equation is 20 times 1. So we got the answer is 20 dB. So for the number 3, 1 plus JW per 5 over 1. So the 5 is P. So we go to the refer, P and W, P like this, and the graph is like this. Go under. Okay. So the equation is negative 20 times N. So we got negative 20 dB. So for the number 4, 1 plus JW per 20 power by 2. So the P is 20. So we go graph, same like the number 3, go down. The graph is go down, we refer. So the equation, negative 20 times 2, we got negative 40 dB. So we continue to the graph. So we must label the graph. So for the axis X, 1, 10 and 100. So axis Y, 60, 40, 20, 0, negative 10, negative 20, negative 30, negative 40 and negative 60. So first thing first, we should plot is for the number 1, 0.15. So for the 0.15, we go straight line. Alright. So for number 2, JW, we start with negative 20 and go up unlimited infinity. So because it's JW for number 2. Alright. So for the number 3, starting with 0 and go to the axis X and plot in 10 and go through axis 40. Okay, axis 40. Go down to the axis 40. For the number 3, 1 plus JW per 5. And for the number 4, wait, alright, for the number 4 is the same, but we go to the axis 10 for the second. This and go down and into the negative 60 in axis Y. So we got the 4, 1 plus JW per 20. So for the final, we got the equation negative 16.48 minus 20 plus 0 plus 0, and we got the answer is negative 36.48. So for the starting point, we got negative 26.48. We go up and go to the 10 and straight at the second 10, and the answer is same like the number 4 for the final. So we just go down. Okay, that's all for me. Thank you.
Hello everyone, my name is Muhammad Ifandi bin Muhammad Sidi and register number is B1125102218. Today I will present about phase plot. To plot the phase board plot, we break the transfer function into 4 terms and find each one's phase contribution. Term 1, constant 0.15 contribute 0 degrees since a constant has no effect on phase. Term 2, the 0 j omega contribute a flat plus 19 degrees since n equal 1. Term 3, the simple pole 1 plus j omega over 5, break point at p equal 5. Lower frequency is P over 10 equal 0.5. Upper is 10P equal 50. Phase stay at 0 degree until omega equal 0.5. Slope down to negative 90 degree by omega equal 50. Term 4, the repeated pole 1 plus j omega over 20 square. Breakpoint at P equal 20. Lower frequency is P over 10 equal 2. Upper is 10P equal 200. Phase stays at 0 degree until omega equal 2. Slope down and twice as steep to negative 118 degree by omega equal to 100. Adding all 4 lines together give the overall phase response, moving from positive 90 degree at low frequency to negative 180 degree at high frequency. Next, I will present for the phase plot. We plot each component of the transfer function separately on the semi-log graph using degrees on the vertical axis and frequency omega on the logarithmic horizontal axis. The purple line represents the 0 at the origin. Since a 0 at the origin always contribute a constant phase of plus 90 degrees, this line stay flat at positive 90 across the entire frequency range. The red line is our 0 degree reference line. It helps us see clearly how far each component shift away from 0 phase. The blue line represents the simple pole at omega equal 5 radians per second. Its phase start at 0 degree at low frequency, decrease gradually through the corner frequency and flattens out the negative 90 degrees once we pass about 1 decade above the corner frequency, around omega equal 50. The green line represents the repeated pole at omega equal 20 radian per second, which is square in the transfer function because it's a second order pole. Its phase shift is twice as steep as a normal pole. It also starts at 0 degrees, drops more sharply through its corner frequency, and settles at negative 180 degrees. Since a repeated pole contributes double the phase change of a single pole. Comparing the blue and green lines, we can see that the green line falls faster and reaches a lower final phase value, which makes sense because the repeated pole has twice the order, and therefore twice the phase contribution compared to the single pole represented by the blue line.
Assalamualaikum and hello, my name is Siti Nur Fatimah binti Ahmad Harun and my case number is B11251022. Now I want to present and talk about analysis transfer function for A. Firstly, we're looking at a magnitude ball plot and plot in a semi-graph. So we're looking at a final line. It's a starting point at a omega 1 is equal to negative 16.48 dB. So next is erasing at a positive 20 dB over DC until omega 5. It reaches negative 2.5 dB. So it's next is a flat at a negative 2.5 dB from omega 5 to omega 20. So it's lastly is a drop shape at a negative 40 dB over DC, a slope after omega equal to 20. Next is we looking at a phase void plot. Looking at firstly, we look at a zero original. So there is a constant positive 90 degree contribute. Next, second, simple pole omega 5 for phase convention 0 degree is equal to negative 90 degree century at omega 5 and range for omega 0.5 to 5. Next, double pole for question for line 4. So omega 20. So phase transfer for 0 to 2 negative 190 degree. So centered at omega 20 and range omega 20 to 200 is double weight. And overall phase strength is cut net positive 90 degree at low frequency, decrease processes and emit negative 190 degree at a high frequency. So that's the cross 0 degree somewhere because get the two corner frequency for this graph. That's all. Thank you.
Okay, next, I want to explain about magnitude dot plot to transfer function method. The magnitude dot plot is obtained by first expressing the transfer function in its standard plot form. The system gain, pool zeros, and breadth frequency are then identified. Next, the initial magnitude and slope are determined, and the effect of each pool and zero is applied at the corresponding corner frequency. The magnitude response is calculated indivisible over the selected frequency range and plot on a logarithm frequency scale. Finally, the complete dot plot is interpreted to analyze the system frequency response.
Next slide is how to calculate ball plot for question F to transfer function. Firstly, we're looking at number 1 for line 1 is for passing x is omega 1. So the line is similar to about the referable ball plot for column 2 is the same. So that means it's j omega n. So n is equal to for passing x is 1. So only j omega. Next is second line is a constant. Constant is a zero slope. So it's zero slope. How to get a zero slope? Before the line, we know that a increase slope is positive 20. So we minus 20, we get a zero slope. So with a negative, that means for the ball plot, that means equal to 1 over 1 plus j omega over p. That means 1 over 1 plus j omega over 10. Because the point, starting point for line 2 is 10 omega. Thirdly is for line 3 is in decrease for negative 20 slope. So how to get a negative 20? That means we forget a zero slope. So minus 20, we get a negative 20 dB over DC is a slope for line 3. That means it's a negative. We equal to get a referral cable. We know at 1 over 1 plus j omega over p. So 1 over 1 plus j omega over 50. So the first, because 50, because that first point, the second point for line 3 is a 50. So it's a p is a 50. So the transfer function for this ball plot is h omega j omega over 1 plus j omega over 10 multiply 1 plus j omega over 50. Thank you.
Now, I will present about analysis 1C. The item 1C is given dot plot. From item 1C, we would backward from the given plot. We see three slope chains, flat to plus 20 at omega 1 indicating 0, plus 20 back to flat at omega 10 indicating a pole, and flat to minus 20 at omega 50 indicating a second pole. This gives the general form h of j omega equals k times 1 plus j omega over 1 plus j omega over 10 times 1 plus j omega over 50.
Well, it's going to be the end of the slides, the conclusions. So the transfer function h omega fully characterize a circuit frequency response. Dot plots simplify complex frequency analysis through logarithmic scaling and straight line asymptotes. Third one, 0 as origin give a permanent positive 20 dB rise and positive 90 degrees phase shift. Fourth one, a single pole introduce a negative 20 dB slope change, a double pole introduce negative 40 dB. The inverse process reading h omega from a board plot is achievable by tracking slope change at each corner frequency. And the last one, in exact curve, deviates slightly from the status at corner frequency negative by approximately positive negative 3 dB for single pole zeros. Nothing much. I just want to say thank you for my teammates, Group 21. Thank you to Puan Shuhada for teaching us this subject, Advanced Electric Circuit, and hoping that we can get an Ace for this subject. And we're really, really grateful for having you as our lecturer. And yeah, I see you guys in the next video. Thank you guys. Bye.